Okay, so we're going to focus on what is known as state space modeling of dynamic systems. We'll go through an introduction, then we'll look at state space equations, and then we'll put those in matrix form. We'll also see a block diagram version of those, and then we'll try and do example 1. Maybe we'll get to example 2, and if not, we'll do that on Wednesday. Okay, so state space modeling is a very powerful technique in general for analyzing and understanding dynamic systems. This is very frequently used in solving differential equations in computers. If you ever take like a numerical differential equations class, you'll learn about Range-Kutta methods. Those methods are all designed for first order differential equations, and then that's what we end up using. Well, when we go to state space, we convert from higher order down to first order. And then we can then run those through computers. We're going to go through several different definitions about what a state is, what a state vector is, and then what state space is. And then we'll go and look at what these equations are, put them into matrix form, and then into the block diagram. Okay, so the state of a dynamic system is going to be the smallest set of variables needed along with the input to completely determine the behavior of the system. So we'll say here that the state of a dynamic system is the smallest set of variables needed along with the input to completely determine the behavior of the system. And so we can call those, or we call them, the state variables. So we'll just say these are called the state variables. Okay, and so for vibrating systems, the state variables are going to be the displacements and the velocities. So you'll need the displacements and the velocity. You need to know both of those in order to know to completely determine the behavior of the system, plus the inputs as well. So these are the displacements and the velocities. The displacements tell you where the system is at a given time. The velocities tell you where it's going at a given time. So for a harmonic oscillator, if you know the displacement at a particular time, you'll know where it is. And if you know the velocity, then you'll know, is it going to move, in which direction is it going to move next? So you know where it's going. That's everything you need to fully determine what's going to happen to the system, provided you also know the input. Okay, so then the state vector, this is just a vector whose components are the state variables for a given system. So there's not really much else to say there. This is just a vector whose components are the state variables for a given system. Okay then, so state space then is for n state variables. For n state variables, the state space is the n-dimensional space whose axes correspond to each state variable. So it's just some higher dimensional space in which the system lives, and where all of the state variables live. So we can say that for n state variables, the state space is the n-dimensional space n-dimensional space whose axes correspond to each state variable. So for a harmonic oscillator, the state space is if you were to plot velocity versus displacement, that would be the state space. Okay, in state space analysis, we're going to be concerned with three types of variables. The first is what is input variables. So the inputs to our system. The second is going to be our state variables. And the third is output variables. Okay, for a linear time invariant system, the state equation is going to have the following form. We'll have our first state variable x1 dot. This is going to be equal to a11 times x1. That's just the first coefficient times the first state variable, then plus some a1, 2 times x2, plus dot dot dot, plus some a1n times xn. So that's our n state variables. And now we're going to add inputs. So we're going to have plus b11 times our input u1 plus a b12 times u2 plus dot 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 plus b1r times ur. So we have n state variables and r inputs to the system. We're going to have n state equations. So we're going to end up down here with an xn dot equal to a n1 times x1 plus a n2 x2 plus dot 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 plus a and n xn plus some b n1 times u1 plus b n2 u2 plus dot 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 plus b n r times ur. So we've got n state equations. Each state equation can depend on all n state variables. And then we've assigned here r inputs to the system, where n and r don't have to be equal. They could be equal, but they don't have to be. Usually they're not equal. Okay, our output equation is going to have a similar form. This is going to be output y1 equal to some c11 times x1 plus c12 times x2 plus dot 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 plus c1n xn. So this is our our output variable y1 being dependent on all of the different state variables. And then it can also depend on the inputs, and so we'll get a d11 times u1 plus d12 times u2 plus dot 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 plus d1r ur. So our output variables can depend on both the state variables and the output variables, or they can at least. The output may also be just a state variable itself, or it may be some combination of them. We're going to have here m outputs, so we're going to have these little vertical dots. This can go all the way up to ym. This is going to be equal to c m1 times x1 plus c m2 times x2 plus dot 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 plus c mn xn plus, in this case, dm1 times u1 plus dm2 u2 plus dot 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 plus dmr ur.
For the state equation on like the bottom right set where it was like the B's, were those supposed to be M's or N's?
Those are, let me double check. Those are n's.
N's?
Yeah, those are n's. Those are, so like this is nr, this is an mr. Because
The first one is N and N, like A N N.
so this is a and n.
Okay.
Yeah.
Just making sure.
Yeah, so we're about to put this in matrix form, and then we'll talk more about, I'll come back to that question. Okay, we can convert this into matrix form. we'll get x dot, that's our state vector, is equal to some capital A, that's a matrix, times our state vector x plus the matrix B times the input vector u. That's our state equation. And then our output equation y is equal to some matrix C times the state variables plus a matrix D times the inputs. And then here, the state variable x is going to be the vectors x1, x2. It's going to be a vector of x1, x2, dot, 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 up to xn. So it's an n by 1 matrix, or in this case, just a vector. The matrix big A is going to be the collection of all those little a's. So we'll get A11, A12, A21, A22. Then I'm going to fill this up with dots. And then we'll get A, N1, A, N2, A, N, N down in the bottom corner, A, 1N, and then A, 2N. So A here is an n by n matrix. X is n by 1. The input u, this is going to be a vector of u1, u2, dot, 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 u-r. So u here is going to be r by 1. And then lastly, the matrix B. This is just a matrix of B11, B12, B21, B22. Here we'll have B1R, B2R. Down here we're going to have BN1, BN2. And way in the bottom, we're going to have B and R. So here B is an N by R matrix. Okay, for the output equation, first we're going to get y. Y is just going to be a vector of outputs. So y1, y2, to ym. M does not have to equal to n. Then the C matrix, so y here is m by 1. Our C matrix is going to be equal to C11, C12, C21, C22, dot, dot, dot. Then C1n, dot, 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 C2n. Many dots. And then this will be CM1, CM2, And then lastly, CMN, such that C here is an M by N matrix. And then the last one, D, we just get D11, D12, D21, D22, dot, 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 D1R, dot, 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 D2R, and our many dots. We have DM1 here, DM2, and then DMR, such that D is an M by R matrix. And then we'll see what this actually looks like when we do the examples. Okay, so matrix A is called the system state matrix, B is the input matrix, C is the output matrix, and then D is called the direct transmission matrix. And then the vector X is the state vector, vector U is the input vector, and then vector Y is just the output vector. Okay, we can also express the set of these equations in a block diagram, which I will get started down here. First, we're going to have our input vector U of t. We're going to put our input matrix B over here. U is going to feed into B. It's also going to feed into the direct transmission matrix D up over here. We're going to feed B into a summing junction. And we'll come back and fill in the rest of the summing junction in a moment. Out of this summing junction, we're going to get the time derivative of our state vector, or this x dot vector. It's going to feed into an integration term with integral dt. And then out of that, we're going to get the state vector x the state vector is going to go back and feed into that summing junction. The first thing it's going to do, and it's going to pass through the matrix A first. So x is going to go into A. So then going to be added at the summing junction. And then x also goes into the output matrix C. The output of the output matrix is going to go into another summing junction. It's going to sum with the output of our direct transmission matrix. And then out of that, we're going to get our output y of t. So this is the block diagram representation of the matrix form of the state equation and the output equation. Okay, some comments on state space. So we're generally going to be looking at second order or higher order differential equations. We're going to convert those into first order. That's going to give us our set of first order differential equations. That is the state space form. The number of first order equations needed is equal to the order of the original differential equation. And so if you have a second order, you're going to need 2 equations. If you have a third order, you're going to need 3 equations. If you have a set of coupled differential equations, you can convert those into state space, and then you're going to have the number of first order equations will be equal to the summation of the orders of each equation. So if you have a second order and a third order equation coupled together, you're going to need 5 first order equations for your state equations. The number of state variables is also equal to the sum of the orders of those original differential equations. And then if you have an nth order system, the state space form is going to consist of a set of n first order differential equations. Okay, so the benefit of state space modeling is that it reduces higher order differential equations down to first order differential equations, which are things that are relatively easier to solve directly. The disadvantage is that by doing that, you pay the price of having extra equations. You now have more equations that you have to deal with. And so you can reduce the complexity down to first order, and then you pay the price by having n additional equations, or n minus 1 additional equations to solve. All right, we're going to go through the first example, and then we'll do the second example on Wednesday. We may not finish this one, but we'll at least get started. We're going to illustrate state space modeling through a few examples. And then after we get through, we're going to start off with just looking at 2 differential equations, and then we're going to look at transfer function matrices. Okay, so we're just given a third order differential equation shown here, and asked to convert it to state space. We have here A times x triple dot plus B x double dot plus C x dot plus dx plus f of t shown here. So it's a third order differential equation with some input as shown there. So we're going to need 3 state variables and then 3 state equations because it's a third order differential equation. So we're just going to write that down here. Say that the system is third order. So we need 3 state variables. and 3 state equations. To this end, we're going to say that that x1 is equal to x, x2 is equal to x dot, then x3 is equal to x triple dot. Oh, sorry, it's going to be x double dot. So we've now defined 3 new variables. These are going to be our state variables. So we'll have x1, x2, x3. And we've set them equal to x dot, and x double dot. So that in general, you're going to choose, since we need 3 state variables, we're going to always start with the 0th derivative and then set the second one to the first derivative, the third to the second derivative, and then so on up to n minus 1, which will be equal to the n minus 1 derivative. We can take the derivative of these with respect to time. We're going to get x1 dot is equal to x dot, but we already defined x dot as being equal to x2, so this is equal to x2. Then x dot of 2, this is equal to x double dot, which we already defined to be x3. So then this is equal to x3. Then x triple dot, x3 dot, this will be equal to x triple dot. So from here, we can say that x1 dot is equal to x2. x2 dot is equal to x3. And x3 dot is equal to x triple dot. And these are our state equations, although we're not done yet. Okay, so from here, we're going to take the original equation and we're going to solve for x triple dot. So we'll just say, next, we take the original system and solve for x triple dot. We're going to use that to then find out what x3 dot is. So just to rewrite our equation, we had ax triple dot plus bx double dot plus cx dot plus dx is equal to f of t. We can solve then for x triple dot, and we're going to get x triple dot equal to minus b over a times x double dot minus c over a x dot minus d over a x plus 1 over a times f of t. And using our state variables, using the state variables, we'll write that x triple dot is equal to x3 dot, which is then equal to minus b over a times x3 minus c over a x2 minus d over a x1, and then lastly plus 1 over a f of t. All right, then thus, the state space equations are first we get x1 dot, and that's equal to x2. Then we get x2 dot equal to x3. And then we'll get x3 dot equal to minus b over a x3 minus c over a times x2 minus d over a x1 plus 1 over a times f of t and that is the state space equations for this system. So we have 3 equations. They're all first order differential equations, but we now have 3 of them that we have to deal with. Okay. And then in matrix form, we can write here our system state matrix A. This is going to be 0, 1, 0, and 0, 0, 1. And then lastly, minus d over A, minus c over A, and then minus b over A. We're going to say that z is our state vector because we already used x. We're going to say z is the vector of x1, x2, x3. Then z dot. This is x1 dot, x2 dot, x3 dot. Our input matrix B is equal to, so it's a column vector of 0, 0, 1 over A. And then U is simply equal to f of t. It's just a scalar because there's only one input. And then we can write this out as z dot is equal to A, z plus B times f of t.